This is first module of chapter 2. The chapter 2 is divided to interpolation, particularly polynomial interpolation. Lot of interpolation methods are available in literature. Among them, the most important methods are discussed in this chapter, in chapter 2. In first module, we shall discuss about Lagrange interpolation method. That one very simple, that means the concept of this method is very simple. So, that is why we consider this method in module 1, but the question is what is interpolation? The interpolation is a problem where a table of values of x and y are given, where y equal to f x. The function f x is not known explicitly, but a table of values of x and y are given. The main problem of interpolation is to determine the value of y for a given x. The x lies between the minimum and maximum of the given values of x. So, this is the main problem of interpolation. So, in next slide we formally define what is the problem of interpolation and their uses. Now, we formally define the problem of polynomial interpolation. So, in this problem we assume that y equal to a function of f x, but this function is not known explicitly, but a table of values of y is given for a certain values of x, say x 0, x 1, x 2 up to x n. These are called the arguments, and there is no other information available for this function, but the condition f of x I equal to y I, this should be satisfied for all I equal to 0, 1 up to n. So, this is the major condition of the interpolating polynomial. The problem of interpolation is to find the value of y, that one is equal to f x for a given values of x, say x bar. Obviously, the value of x bar is unknown. So, in interpolation polynomial, particularly in polynomial interpolation, a polynomial phi x is called interpolating polynomial if y equal to f x equal to phi at x I, where f is the explicit unknown function, but phi x is a polynomial. That means, the phi x approximate the given function f x, and these two values, that means the value of the function at x I and the value of the polynomial at the same point x I must be equal, and this condition should be satisfied for all values of I equal to 0, 1 up to n. And other condition is that the kth derivative of f, the function at the point x bar, is equal to the kth derivative of the polynomial at the same point x bar for any or for particular finite values of k, and x bar one of the values of x 0, x 1 up to x n. Every interpolating polynomial must satisfy this condition, and there is other important condition. That condition should be satisfied by every interpolating polynomial. That one is stated below. If the function f x is continuous on a certain interval, closed interval a b, then for any pre-assigned positive number epsilon, that one should be greater than 0, there exists a polynomial phi x such that the difference between the absolute difference between the function f x and the polynomial phi x should be strictly less than epsilon for all x between the open interval a b. This expression actually implies that the phi x is bounded by the function f x minus epsilon and f x plus epsilon for some given epsilon. So, this figure illustrates the above theorem or the bounds of the interpolating polynomial. The medial curve actually represents the given function y equal to f x. The curved line represents the approximate polynomial y equal to phi x, and the most upper curve represents the upper bound of the polynomial as well as the function, and that one is equal to f x plus epsilon, and the lowermost curve represents the lower bound of the polynomial as well as the curve, and that one is equal to f x minus epsilon. So, this diagram actually keeps the upper and lower bound of the function and the polynomial. Now, we deduce the Lagrange interpolation polynomial, that means, we shall use the Lagrangian method to derive a polynomial. So, we first define what is the Lagrange interpolation polynomial or problem of Lagrange interpolation. Here also we assume that y equal to f x be a real valued function, but the function is not known explicitly and it is defined on the closed interval a b, and y I equal to f of x I. This is true for all I equal to 0 to n, and we assume that the following table of values is available. That means, the values of x are x 0, x 1, x n, and the values of y are y 0, y 1 up to y n. This table is given. So, based on this table, we have to construct a polynomial phi x whose degree at most n, that means less than or equal to n, and this polynomial must satisfy the condition phi of x I equal to y I for all I equal to 0 to n. This is the main, the equation 2 is the main condition of any interpolating polynomial. So, the polynomial phi x is called the interpolation polynomial based on the Lagrangian method, and it may be noted that if all the points are collinear, then the polynomial phi x is of degree 1. That means, this becomes a linear polynomial. That means, for a given set of values, the number of points is n plus 1. The interpolating polynomial is either linear or is of degree at most n. Now, let us consider the polynomial phi x in the following form in Lagrangian formula. Phi x is equal to I equal to 0 to n Lix into yi, where each Lix is a polynomial in x of degree less than or equal to n. In general, it is a polynomial of degree n, and this polynomial Lix is called the Lagrangian function. But for the polynomial phi x, this Lagrangian function Li must satisfy the following condition. The condition is this: Li at xj equal to 0 for different I and j, and it is equal to 1 for equal I and j. So, this is the main criteria for the Lagrangian function Lix. Now, this condition implies that the polynomial Lix is 0 at the given points x 0, x 1 up to x I minus 1, and then x I plus 1 to x n, and it is equal to 1 when x equal to x I. So, based on this condition or based on this assumption, we assume that Lix equal to a I into x minus x 0, x minus x 1 up to x minus x I minus 1 into x minus x I plus 1 up to x minus x n. Here all the factors are present in this expression except x minus x I factor, and here a I is a constant and the value of a I is to be determined by using the condition Lix I equal to 1, that was shown in the previous slide. Since Lix I equal to 1, so we substitute the value of x equal to x I in the previous expression in the expression of Lix, and this becomes a I into x I minus x 0 up to x I minus x I minus 1 into x I minus x I plus 1 to x I minus x n, and this is equal to 1. So, easily we obtain the value of a I, that one is equal to 1 by x I minus x 0 into x I minus x 1 up to x I minus x I minus 1 into x I minus x I plus 1 up to x I minus x n. Since the value of a I is obtained, then we can write the value of Lix in explicit form as this one: Lix equal to x minus x 0 into x minus x 1 up to x minus x I minus 1 into x minus x I minus 1 up to x minus x n whole divided by x I minus x 0 to x I minus x n except the factor x I minus x I. So, this is the expression for Lagrangian function Lix. Since the Lix is obtained or this is available in terms of the argument x 0 to x n, then the Lagrangian interpolation polynomial phi x is given by phi x equal to summation I equal to 0 to n Lix y I, where Lix is given by equation 4 and for all I equal to 0 to n. It may be noted that the Lix can be expressed in terms of a product of factors like this: Lix equal to product of j equal to 0 to n, j not equal to I, x minus xj by xi minus xj. The Lagrange interpolation formula can also be represented in terms of other notation. So, for this purpose we assume that Wx equal to x minus x0 into x minus x1 up to x minus xn. That means, all the factors are present in this expression in Wx. Note that the degree of Wx is n plus 1 and it vanishes at the point n plus 1. That points are x0, x1 up to xn. Now, we find the derivative of Wx, the W dash x equal to x minus x1, x minus x2 up to x minus xn and so on. The medial expression is x minus x0, x minus x1 up to x minus xi minus 1 into x minus xi plus 1 up to x minus xn. Note that the factor x minus xi is absent in this expression and the last term is x minus x0, x minus x1 up to x minus xn minus 1. So, note that in this expression x minus xi factor is present all the terms except the middle one. Now, when x equal to xi, then W dash xi equal to xi minus x0, xi minus x1 up to xi minus xi minus 1 into xi minus I plus 1 up to xi minus xn. Only one term is present because all other terms contains the factor xi minus xi. So, that terms become 0. So, this expression nothing but the denominator of the Lagrangian function Lix. So, using this notation the Lagrangian function Lis becomes Lix equal to Wx by x minus xi into W dash xi. So, this is a very simple expression to represent the Lix, the Lagrangian function, and in terms of this notation the Lagrangian polynomial phi x equal to I equal to 0 to n Wx by x minus xi W dash xi into yi. Note that for a set of n plus 1 points, the degree of Lagrangian interpolating polynomial is at most n. That is, the degree of polynomial depends on the number of given points. And second observation is that the Lagrange interpolating polynomial always pass through the given point xi yi, where yi equal to phi of xi, and this is true for all I which is equal to 0 to n. These are the two important observations for Lagrangian interpolating polynomial. Now, let us consider one example to illustrate the Lagrangian interpolation method. Let us consider a table which contains the values of x and f x. The values of x are minus 1, 0 and 1 and the values of f x are 3, 8 and 11. Our problem is to find the polynomial phi x using Lagrangian method and hence find the value of the function f x at x equal to 0.5. So, in this case x0 equal to minus 1, x1 equal to 0, x2 equal to 1, f of x0 equal to 3, this is nothing but y0, f of x1 equal to 8, this is y1, f of x2 equal to 11, this is y2, and let phi x be the approximate polynomial of the function f x obtained by Lagrangian method, and that one is phi x equal to summation I equal to 0 to 2 Lix f of xi. Now, our problem is to calculate the Lagrangian function L0x, L1x and L2x, and these are calculated in the next slide. As by definition of Lix, L0x equal to x minus x1 into x minus x2 whole divided by x0 minus x1 into x0 minus x2. By substituting the values of x0, x1 and x2, we obtain L0x equal to x square minus x by 2 and L1x equal to x minus x0 into x minus x2 whole divided by x1 minus x0, x1 minus x2, and after simplification this becomes x square minus 1 whole divided by minus 1 and L2x equal to x minus x0 by x minus x1 whole divided by x2 minus x0, x2 minus x1, and after simplification this becomes x square plus x by 2. Therefore, phi x equal to x square minus x by 2 into 3, 3 is the value of f x 0 plus x square minus 1 by minus 1 into 8, this is the value of f at x 1 plus x square plus x by 2 into 11, this is the value of f at x 2. After simplification, this reduces to minus x square plus 4x plus 8. So, this is a quadratic polynomial and this is known as the Lagrange interpolating polynomial. Now, from this polynomial we can calculate the value of the function f at 0.5, but as per our knowledge or as per our convention, f x is approximately equal to phi x. That means, f at 0.5 is approximately equal to phi at 0.5 and this becomes 9.75. That means, when the value of x is substituted in the expression for phi x, then the value becomes 9.75. This is the approximate value of the original function f at the point x equal to 0.5. Now, we consider a simple case of Lagrange interpolation method. Here we consider 2 points x 0 y 0 and other is x 1 y 1. That means, for this 2 point we obtain the following Lagrange interpolating polynomial phi x equal to L 0 x y 0 plus L 1 x y 1. This is equal to x minus x 1 by x 0 minus x 1, this is nothing but L 0 x into y 0 plus x minus x 0 by x 1 minus x 0 into y 1. After simplification, this expression reduces to y 0 plus x minus x 0 by x 1 minus x 0 into y minus y 0. So, this is called the linear interpolation polynomial for the interval x 0 x 1. And in general, for any arbitrary point x I to x I plus 1, the interpolating polynomial phi x equal to y I plus x minus x I whole divided by x I plus 1 minus x I whole into y I plus 1 minus y I. This is the linear interpolating polynomial within the closed interval x I to x I plus 1, and this is true for all I equal to 0 to n minus 1. So, we have deduced the Lagrange interpolation polynomial for unequal space arguments, but if we introduce the equal space points, that means if the arguments are equal spacing, that means the length of the interval are equal for each interval, then the above formula becomes simple one. So, for this purpose we introduce a new variable s, which is defined as x equal to x 0 plus s h, where s is a unitless quantity or dimensionless quantity. So, with this substitution and with the condition x I equal to x 0 plus I h, this is defined for the equally spaced arguments. So, for this assumption x minus x I equal to s minus I whole into h and x I minus x j equal to I minus j into h. So, using this value in this notation w x becomes w x equal to x minus x 0 into x minus x 1 up to x minus x n, and this is equal to s h because x minus x 0 is s h, then s minus 1 into h and then s minus 2 into h up to s minus n into h. After simplification, this expression reduces to h to the power n plus 1 into s minus 1 up to s minus n. So, this expression more simpler than the previous expression. Again, w dash at x I, that one also reduces to a simple expression, and w dash x I equal to x I minus x 0 to x I minus x I minus 1 and then x I into x I plus 1 to x I minus x n. The first terms x I minus x 0 becomes I h, second term becomes I minus 1 into h, and x I minus x I minus 1 becomes I minus of I minus 1 into h and so on. So, note that the number of terms in w dash x square is n. So, there are n h. So, after simplification, this expression reduces to h to the power n into I minus 1 up to 1 and then minus 1 into minus 2 up to minus n minus I. So, this term again simplified as h to the power n and factorial n into minus 1 to the power n minus 1 and the last terms are nothing but factorial n minus 1. So, using this notation the Lagrangian polynomial becomes phi x equal to summation I equal to 0 to n h to the power n plus 1 into s minus 1 up to s minus n whole divided by minus 1 to the power n minus I h to the power n into factorial I into factorial n minus I into s minus I into h. Note that the number of h in numerator and denominator are same. So, the h are cancelled from numerator and denominator. After cancelling this term, we obtain this expression summation I equal to 0 to n minus 1 to the power n minus I into s minus 1 up to s minus n whole divided by factorial I into factorial n minus I into s minus I into y I, where x equal to x 0 plus s is. Note that this expression is more simpler than the previous or original Lagrange interpolation polynomial. Now, we present some important properties of Lagrangian functions. The Lagrange function Lix satisfies many interesting properties that are stated below. The first one is the Lagrangian function depends only on the values of arguments, that means the values on xi only, but does not depend on the values of the ordinate, that means the values of the function. The second observation is Lagrangian functions are invariant under linear transformation. That means, if x equal to au plus b, where a and b are constant, then Lix equal to Liu for all I equal to 0, 1, 2, etc. That means, the Lagrangian function remains same under linear transformation. And third property is that one also very important. The sum of the Lagrangian function is 1, that means summation I equal to 0 to n Lix equal to 1. So, these are the three interesting properties of Lagrangian function, and all these properties are proved in the content. So, we have deduced Lagrange interpolating polynomial for unequal and equal space arguments, but it is interesting that for a given table of values of x and y, the Lagrange interpolation polynomial must exist and it is unique. That means, we can say that the Lagrange interpolation polynomial exists and unique. Not only that, for a given table of values of x and y, the interpolating polynomial must be unique and should exist, whatever may be the interpolation method is used. In chapter 1 and first module, we have mentioned that every numerical computation contains some errors, and this is also true for polynomial interpolation. Every polynomial interpolation or interpolating polynomial contains some error, whatever may be the method is used to find out such interpolating polynomial. So, the expression of error for interpolating polynomial is calculated in the next slide. Now, we calculate the error which occurs in interpolating polynomial. This is a very powerful theorem. Here we assume that I be an interval such that all interpolating points, that means x 0 to x n, contained within the interval I, and if f x is continuous and have continuous derivative of order up to n plus 1 for all x within the interval I, then the error at any point x is given by E n x equal to x minus x 0 into x minus x 1 up to x minus x n. This is nothing but w x into n plus 1 derivative of f at the point xi whole divided by factorial n plus 1, where xi is a point which is belongs to the interval I. So, in case of equispace point, the error term is given by E n x equal to s into s minus 1 into s minus 2 up to s minus n into h to the power n plus 1 into n plus 1 derivative of f at xi whole divided by factorial n plus 1, where xi belongs to the minimum and maximum arguments. So, this is the error for any interpolating polynomial, not only the Lagrange interpolating polynomial. This expression is valid for any kind of interpolating methods, but the previous expression has no computational meaning, because the derivative of f of order n plus 1 does not exist, because the function f x is not available explicitly. but this gives the theoretical expression or theoretical meaning, but sometimes we can determine or it is available the upper bound of the n plus 1 derivative of the function, and if it is equal to m n plus 1, then the upper bound of the error term is nothing but m n plus 1 by factorial n plus 1 into absolute value of w x. So, this is the upper bound of the error in any numerical computation or any interpolating polynomial, where m plus n is the upper bound of the n plus 1 derivative of the unknown function f x. In case of two intervals, that means for the points x 0, x 1 and x 2, the upper bound of the error e 2 x is h cube into m 3 by 9 into root over 3, and this is proved in the following portion. The e 2 x equal to s into s minus 1 into s minus 2 into h cube into absolute value of the third derivative of f by factorial 3. It is obtained by definition. For simplicity, we assume that g s equal to s into s minus 1 into s minus 2, that is g dash x equal to 3 s square minus 6 s plus 2, and at extremum g dash s equal to 0, and this gives s equal to 1 plus minus 1 by root 3. And second derivative at s equal to 1 minus 1 by root 3 is negative. So, g s is maximum at s equal to 1 minus 1 by root 3, and it is equal to 2 by 3 root 3. Hence, the upper bound of e 2 x is 2 by 3 root 3 h cube into m 3 by 6 equal to h cube m 3 by 9 root 3, where m 3 is the maximum value of third derivative of f at any arbitrary point xi. Now, let us consider an example to illustrate the Lagrange interpolation method. Here we assume that f x equal to 1.25 minus x whole into e to the power minus x. So, we have to approximate this function into a quadratic polynomial by taking x equal to 0, 0.5 and 1. So, for this purpose we assume that x 0 equal to 0, x 1 equal to 0.5, x 2 equal to 1, and f of x 0 equal to 1.25, f of x 1 equal to 0.75 into e to the power minus 0.5, f of x 2 equal to 0.25 into e to the power minus 1. Thus, the quadratic polynomial phi x is given by this expression. This is nothing but the Lagrange interpolating polynomial phi x equal to x minus x 1 into x minus x 2 whole divided by x 0 minus x 1 into x 0 minus x 2 into f of x 0 plus 1. After substitution of the values of x 0, x 1, x 2, f of x 0, f of x 1 and f of x 2, and after simplification the phi x reduces to 0.864348 x square minus 2.02237 x plus 1.250000. That means the entire calculation is made up to 6 decimal places. So, this is the approximate quadratic approximation of the function f x equal to 1.25 minus x whole into e to the power minus x. Graphically, the function f x and phi x are shown in this slide. The red color line represents the function phi x and the blue line represents the function f x. Note that the two functions, that means the function f x and the polynomial phi x, are almost equal within the interval 0 1. That means these two functions are coincide to each other. Now, let us consider another example to illustrate the Lagrange interpolation formula. Using this method, we can express any function in terms of a sum of partial fraction. So, for this purpose, we consider the expression x square plus 2x plus 3 whole divided by x plus 1 x into x minus 1. So, here we assume that f x equal to x square plus 2x plus 3, and we tabulate the value of x and f x at x equal to minus 1, 0 and 1, because the denominator vanishes at x equal to 1, 0 and 1. So, the table is this one, minus 1, 0 and 1 are the values of x, and the corresponding value of f x are 2, 3 and 6. So, for this table the Lagrange function L0 x equal to x into x minus 1 by 2, L1 x equal to x plus 1 into x minus 1 by minus 1 and L2 x equal to x plus 1 into x by 2. So, these Lagrange functions are obtained by the definition of Lix. So, now by Lagrange interpolation formula, f x is equal to x into x minus 1 by 2 into 2, the 2 is the value of f at minus 1 plus x plus 1 into x minus 1 by minus 1 into 3, 3 is the value of f at 0 plus x plus 1 into x by 2 into 6, the 6 is value of f at x equal to 1. So, after simplification f x becomes x into x minus 1 minus 3 into x plus 1 into x minus 1 plus 3x into x plus 1. Thus, finally, we have x square plus 2x plus 3 by x plus 1 x into x minus 1 equal to f x by x plus 1 x into x minus 1, and using the values of f x, the expression reduces to 1 by x plus 1 minus 3 by x plus 3 by x minus 1. So, we have expressed the expression given expression in terms of partial fractions. So, this is one application of Lagrangian interpolation method. We have defined what is the problem of interpolating polynomial, and we have deduced one important or simple interpolating method or interpolating polynomial, that one known as Lagrange interpolating polynomial for unequal space interval or equal space interval. Now, we have observed that the Lagrangian interpolating polynomial fully depends on the Lagrangian function Lix, but we notice that each Lagrangian function is a polynomial of degree n. So, to compute the Lagrangian function phi x, a lot of polynomial of degree n can be calculated. The number of such polynomial is n plus 1 for n plus 1 arguments. So, to calculate a polynomial of degree n takes lot of times and it is very difficult. A appropriate or suitable method is available to evaluate a polynomial of degree n, that is known as Horner method, and this method takes n additions and n multiplication to evaluate a polynomial of degree n. So, Lagrange interpolating polynomial actually takes lot of calculations, lot of arithmetic calculation, but there is another suitable method which takes a less number of computation, which is discussed in next module of this chapter. That method is known as Newton's interpolation method.